Welcome everyone to today's video. I wanted to continue a little bit with the topic of using GCC for DOS development for vintage computing and also tools. And one more thing, as you have seen in my first part of this, getting the basics working, I also wanted to get some more advanced things working. So in the first part we could do basic things like calling software interrupts for DOS and BIOS services, and also writing to memory, for example writing into VGA memory or other hardware resources, and also initiating this I/O input and output things. And the next major thing is actually hooking up into interrupts, mostly generated by hardware. For those not that familiar with this topic, the software interrupts that we used in the first part are actually, in my opinion, a little bit more of a special flavor of those, because historically, initially, for the most part, they were used by hardware to signal some event to the software, to the operating system, or this close to the metal DOS applications. Using this in software, in my opinion, is more of a special variant of this. Of course, you can read all the details here. Examples for this are interrupts by the mouse, keyboard, timer, storage devices, and of course also graphic adapters historically to signal the end of the frame and signal the vertical retrace. And the most basic things we would want to use this is, for example, a timer, so that we have control over what time it is in our demo application or game, to move things independent of how fast we can draw them. And also later for sound services, for example, if we would write sound data to the sound card, to the sound hardware, that we get a notification when this data was played back and we should load new data into this. Or also, actually in this program today, I started to use this OPL2 or 3 Yamaha FM synthesis as found in the original AdLib, or the more advanced versions later in the AdLib Gold and Sound Blaster Pro 2 and later. So in this example we use a classic timer interrupt to update the frequency on this OPL2/3 frequency synthesis. And also I wanted to drop a note here that actually the wrapper functions for this fm.h and c are actually DOS examples I found on the internet, copyright 1997, 20 years ago, by Ethan Brodsky. I only dropped them in here, and what is amazing is, and why I wanted to present the whole topic of using GCC. With GCC we got to use a very modern toolchain, and we write quite, well, except some assembly stuff, but for the most part totally ordinary regular C programs that we can also copy and paste and share with Linux or Windows programs and such. And another example is this fm.h I dropped in here. I think I did not modify a single line of this. Of course, this does not work with all DOS and Windows examples, because often they are full with their own compiler-specific attributes, like here's this far pointer and such. And of course, this also has this a little bit, but this was already in ifdefs, and we are very lucky that we did not have to modify. Of course, I've not chosen the first example I could find. The first I could find with Google were, in my opinion, too ugly for this. And of course, I've then chosen the one that I, on the first glance, already realized I would hopefully not have to change much. The only thing is to adapt their I/O stuff we define in P to in B, to P to out B, as used in our example. And as far as I remember, that was the only thing I had to modify. So the tricky part, and why I make the video about this, is to hook up this interrupt stuff. And this took way longer than even all my initially toolchain and getting the stuff to work from the first video. Getting all this interrupt stuff probably took 2 or 3 times as long as all the initial enablement. So for this, I have here the get vector and set vector functions. What these do is they get an interrupt vector and set an interrupt vector. The interrupt vectors live in the very beginning of the memory space for x86 CPUs, address 0. And I use my far pointer abstraction here to read your raw values for testing. And you could also set your interrupt vectors like this. However, there are DOS services that, in my opinion, we should also use for the abstraction of it instead of messing around with it ourselves. The very tricky part of this is that these are segment and offset pairs of this remote addressing that I probably mentioned in the first video. So in this remote that we are unfortunately running, we have the 16-bit segments that are shifted 4 bits left to address 1 megabyte of memory with the 16-bit segments and offsets. That makes everything always a little bit tricky because our GCC is not aware of this. And this kind of things always are a little bit time consuming and error prone to trial and error and debug. I modified this multiple times. Initially I had here the set vector to use our address, but I later changed this to use a regular segment offset notation. The reason for this is to have these two APIs accept the same input. Otherwise, I had here earlier our own address space and our own code and data segment. This did not allow to reset the vector to the original value, so I had to modify this later. And I also had to tweak this again and again to really work reliably. The syntax here is a little bit ugly because we return an actual function pointer, although this does not help us so much because due to the nature of the segment offset notation, we often need to pass this around here back and forth anyway. But initially I thought having real function pointers is nice, but so much to the abstraction. So what we do here is we load the API value and calls DOS interrupt. So we let the compiler pass in here AL as interrupt number, push save the extra segment, also load AH, the high part, with the number of the API syscall number, so to say, and then we convert the far pointer. So actually the comment is not completely right. Actually we load far pointer pair or something, just to make this fitting the raw value in hardware and debugging this a little bit easier. So this is 16-bit for the offset part, and as this is returned in ESBX, I add the value of BX to this. You could also OR this, but it doesn't really matter in this case anyway. This is push and pop. We just save and restore here the ES value, the extra segment. And yeah, here's even warning output is raw remote segment offset. That is correct. Just this comment was misleading. And to set this, it's exactly the same. And of course, this looks totally straightforward and easy, but debugging, by the way, why is this here? But debugging this took a little bit of time and changing the API format a little bit and stepping through this and such. So, but to use this, it's still a little bit tricky. So we have a interrupt service routine timer here, ISR timer. And also this, I think this use was needed, otherwise the compiler may not output it. And also this is a little bit extra tricky because, as I mentioned earlier, this details took all the time to get this working and debug this, because naively you would write here just ISR timer. However, I will tell you in a minute why this doesn't work. And also we define here another function name here in the assembler part of this. More to this in a minute. And I probably will try in the future. It looks like maybe the latest GCC 7 or so may have pure or naked or so attributes for interrupt functions, but more details to this in a minute. So to set this up, we actually need to know the value of our code segment. Actually, we could hard code this because we are DOS.com executable and are usually loaded to the same address. However, the more universal way to do this is to actually load our code segment and save it here to a char pointer. Does not matter so much. I only use a char pointer. More correct would be a void pointer or function pointer. But with those we can't do arithmetic. We need to do arithmetic on this. All of this is a little bit more verbose than it needs to be. This is only for debugging and testing. There are actually two timers. Interrupt 8 is a hardware interrupt of the programmable interval timer of the PIC of the PC. But there's also a software interrupt hex 1C that is used to distribute this timer value to additional software to get notified by this. And I tested both and I decided running in DOS it may be nicer to cooperate with this interrupt service on the DOS interrupt or DOS BIOS interrupt of this. So I output here maybe both ES8 and this timer one just for testing and trial and error. And we need to save the original value, and also as we should be cooperative with other programs and resistant services like maybe emulation things for gamepads and such, and also mouse services and such, or whatever, maybe hooking into this already, we should continue calling this. So not only to restore it, but also to call it, we need to save it. And this may be a real, this is a real void function pointer. First we use the DOS service to get the interrupt vector that's currently in place here, and then we use the DOS service to actually set it. And as I said, this is slightly tricky and a little bit of totally ugly casting here. And that comes from using function pointers instead of integers as such. But basically, to do a nice arithmetic, we use our code segment. By the way, theoretically, we maybe want to use an unsigned, but signed, but doesn't really matter so much here. The high bits are shifted up anyway. And so we shift this 16 bits up to the high part of the segment offset pair, because this is the offset in our code segment. So this is a code segment and offset pair. And due to the, in quotes, nice API, we need to cast it a little bit ugly back to a function pointer. And yes, this works. And then for a test, we get it again just to see that we set correctly. And that's it for the interrupt part. Then we just use the OPL2/3 to reset and load here patches and play a tone with a frequency that we will modify in the timer. And then we just have an endless loop that we never quit in this example. This part is nice and tidy. And after debugging this, all of this works. The really tricky part is the interrupt service routine. The problem is, what I also forgot and only found out by debugging, of course, is that all the C functions have already prologue and epilogue, meaning they already save registers and manipulate the stack pointer. And I thought it could be enough to skip the epilogue by using the interrupt return here, but that didn't work. And to adapt for this, we do not use the actual C function pointer. This is why I have an underscore ISR timer. We define a actual global ISR timer here of type function that is skipping all the function epilogues that the compiler may generating for us. Of course, this is slightly wasteful. We waste here a few instructions that we're not using, but that's what it is for now. And we can also use this int3 instruction to trap in the DOSBox debugger. So of course we should push all of what we're using to the stack, and then as per the registered interrupt service routine segment offset pair, but we should also restore data segment. For some reason that is somehow not necessary in DOSBox, maybe because this is the only program that's running. However, I think it was necessary running in real MS-DOS in QEMU for some reason. Maybe it's setting up the data segment differently, or maybe sometimes some other service is running. Anyway, I think the correct thing to do is to set up our data segment. I simply copy this from our code segment, which is the same in our case. Then we increment the frequency. Test print something that does not work reliable, and this is not safe. You should not do this. But for our test visualization today, it should probably work. The reason for this is we are interrupting the normal program flow here from the interrupt at any random point in time. And at this time, we may actually be running in the MS-DOS services already if our program is printing something or reading something from disk. So it's not safe to call the DOS services. Actually, there is a flag that you can read from memory. Some is MS-DOS running. You could theoretically use this to check if it's safe at this time to call into the DOS services. So what is extremely tricky, I intuitively have written it like this, and as I showed you the final result, we are already giving this away. And this is the extremely tricky part that took me hours to debug, because we are running in this code 16 GCC mode that instructs the bin utils assembler to use the 66 hex operand size prefix of x86 instructions, is why this was not working. Because due to this, our call here, as I said earlier, we should call the original function to also do their things. And if we want this to work, because this is expecting to run in a interrupt context, we need to simulate this by pushing the flags that a normal function call would not do, and then we can just call it. However, this did not work because this call was doing a 32-bit call, so to say, and doing the 32-bit call frame adjustments. And for this to work, we need to switch back to real 16-bit real mode code. And then these functions are not generated with a 66 override prefix. And then the stack adjustments work as expected. Again, this may look totally simple, and if you do this kind of assembly programming every day, of course you may say this is of course totally as expected, but this also highlights why assembly programming is difficult. Most of the stuff you write will assemble and it will do some random nonsense or controlled nonsense, at least not what you would expect it to do when you just naively write the instructions and do not overthink all of the consequences of the bits and pieces happening. The same goes for this interrupt return. The interrupt return was also not working, so only one interrupt was working and then my whole emulator state was messed up. And also this took another hour or two to debug. And the problem here is exactly the same, that we need a 16-bit real mode interrupt return without the 66 hex operand size override. Because the 32-bit interrupt return is restoring the stack with all the 32-bit values and not the 16-bit real mode values. And also note the fine difference of having the code 66 at the second instruction, because to restore our values here with push A, we are actually pushing all the 32-bit register values. For this to work, of course, we need the code 16 here at the second line so that our pop A is restoring all our 32-bit values as we have stored. So we only want a 16-bit interrupt return, and after this, of course, we need to switch back for all the other GCC generated stuff that may follow to honor this special assembly mode. So these are the fine details here that I wanted to present today for your DOS vintage programming stuff and that I will publish now. I think with this you have most of the things at hand to do all this tricky hardware stuff. And let's run this. Okay, this may actually be with the video encoding. This may actually consume too many cycles with video running. Oops. Yeah, when the audio is distorted, then we are running out of cycles for the emulation. And if you want to debug this, so I compiled DOSBox with debugging, and then it's always showing this debugging window here. By the way, this is somehow not getting too small to be readable, this window here, but otherwise it doesn't fit onto the 1080 video recording. So this is a famous emulator window, alright, with output it's slightly distorted. So then we call debug for sound, and then we start in this debugger. Unfortunately, with some ALSA printouts here, the view is slightly distorted. This is a pain you need to live with this kind of tool. So as we do not want to single step through this, we can trap on this int3 instruction. We could also trap on the interrupt, but then we may get other things that are running first. So I have this int3 here actually. So trap on this int3, breakpoint int3, set interrupt breakpoint at int3, and then run F5. Actually, this is not trapping. No, maybe we didn't resave it. So now we have the interrupt here highlighted. You always see the change registers like in many assembler debuggers. Here you see the data segment, or at least if I press Alt D, you see the data segment. And here you see the instructions. And this is the machine code here. Here, as I said in the first video, CC for int3. And then push AD is 6660. Here you see the 66 hex operand override that I talked about. And here is loading the code segment to data segment. Here comes our frequency incrementing. So we can now step through this with F10 and we see all the registers updated there. By the way, this is how, as a short introduction to assembly language, machine code, and this is how especially RISC processors work, by loading a value into a register. This is memory address 2698 from our data segment, which DOSBox nicely shows here as having the value C8 right now. This is our frequency. And then we add the value, immediate value 2, that you see by the way here, this immediate encoding, meaning this constant is encoded in the instruction. Again, with the 66 operand size override here, add EAX immediate value 2, and then we store it back into the memory again. This extra store is probably generated because I have here a volatile. I think it sometimes was not updating correctly. It probably was optimized away by the compiler because the compiler thought it's not needed later anymore. This is why you then need this kind of attributes like volatile for things to be really stored. And then we save it again to this location and load it again. Okay, it's slightly unnecessary, but that's what we get for using volatile. Then we call into FM playTone and we call printf. Here's one call, here's another call. And now I already stepped over it so quickly it goes. So here's our call to the original interrupt vector that we obtained first before registering our own. Here you see the instructions push F and call do not have the 66 operand over right here. All the others, as you can see, have them, 66 here, not here, and here it starts again. And this is what I meant earlier, that this is important, otherwise our stack becomes out of alignment here, and out of alignment meaning having the registers not saved at the correct place because we call this as real 16-bit remote, and otherwise with the 66 operand overrides this is a 32-bit instruction pushing way too much 32-bit values on our stack here. Stack meaning here, stack pointer. And then this does not match with the real mode code running there. And also here's our restore of all our saved values. And after this, you see our stack pointer is FF82, which should be the same as we had when we arrived to the interrupt. Here is our interrupt return. And here I continue with F5. And now we are here again at the next interrupt already, just an 18th of a second later. And now we could check again. We arrive in our interrupt service routine with FFBE. And if we step over this again, the second time, you see we arrive at the end with FFBE. If this would not be the case, we would return from our interrupt function with a stack not restored in correct order. And the interrupt return would restore the wrong values, and the program that continues would continue with the wrong values, and this would crash and burn relatively quickly in a matter of instructions or two. And also, again, this call would not work if we, let's do this again, F5 and step over this. And if we would not have the code 16 here, this would not call this remote function with the correct stack placement of the flags and restoring this correctly here for us to continue, because when we continue here, you will see one step here. We are at FF9C with our flags pushed. Then we have our original call that is returning with an interrupt return instruction ERET. So if we step over this FF9C, and we have this interrupt return of the original vector also restored our flags that we pushed here. And again, this needs to be in proper code 16 order for this to work. So that's it for today, the extremely in-depth interrupt service routine and more processor hardware details. And let me remove the int3 again and run this without debugger. And you can see here's this ISR printed that, as I said, does not work reliable in all environments due to the nature of the unsafety of this. And also our frequency, I hope it was hearable on the video, was increasing due to the reprogramming of the OPL2/3 frequency modulated tone there, the sine wave. I hope you liked this in-depth x86 assembly, machine code, interrupt service routine. You can also use this kind of abstraction for other RISC machines, ARM, MIPS boards and such, and also for programming in the Linux kernel, of course. Just it's protected mode there with all the ugly segment offset stuff in the rear mode. However, of course, this is much more simple, and a real Linux, BSD, Windows or macOS kernel is way more complex in other ways of all the APIs around it and PCIe and all the details of this. But the general concept is the same there. So I hope you enjoyed this video. I have one more of this kind coming, and I hope you learned something. As you know, the YouTube algorithm likes when you share, like and subscribe, and I hope to see you soon for the next videos to come.